desktop systems that extrude, like they're basically like hot glue guns on robots. But what we're talking about is actually there's lots of different ways to create an object layer by layer. So there's lots of technologies out there. We'll talk about them. But in general, what they all have in common is that we're taking a 3D model and we're going to build it from the bottom to the top, layer by layer. There's lots of different ways. And you'll notice the word additive is really critical here because it's to oppose it to subtractive manufacturing, the more conventional, I start with a giant chunk of metal and I'm going to mill or machine away. I'm going to subtract material to get to the shape I want. Whereas here, we're going to add material selectively to get to the shape that I want. So again, in general, what all of these processes have in common is some three-dimensional model on your computer, a digital file, and we're going to slice that into layers and then lay down material layer by layer to build the object. And this is something we've been doing a long time in human history, actually, right? We've been always thinking about creating complex, contoured, three-dimensional shapes by slicing it into layers and then assembling them. So instead of doing the old cartography way, now we're making, contour maps. We've just basically replaced that with robots and shrunk the layers down to really make them very fine so we're able to create a really nice representation of three-dimensional shapes. So think about it in that context. So again, as I mentioned, we're all familiar maybe with this idea, right? I'm going to feed some plastic in through a nozzle, like a hot glue gun, and I'm going to build this object layer by layer. And this is actually a time lapse from our lab of us printing, of course, the hokey birds. You can sort of see the shoulder, right? The elbows there. And you'll see that black material is this supporting material that we'll wash away. It allows us to create shapes like the turkey neck that overhang and support each other. But we can, quickly make prototypes and objects, right, with this technology. And this technology has actually been around for 40 years now. We're all going on year 50 here pretty soon. But that's just one way. We call that technology material extrusion. Right? I'm going to take some plastic and I'm going to extrude it selectively. And we should mention, by the way, that in that phrase, extrusion, there's a whole bunch of materials. We actually have a local company in town, Blacksburg, called Cell Inc., that uses that same principle, but it's printing biocompatible materials to think about bioprinting, extruding biologically compatible materials that can be embedded in the human body. So there's lots of different ways of that idea of extrusion. But what you might not know is that's just one of 7 different ways of printing. So very big classifications, and there's lots of companies and lots of materials inside each one of these. And they are again, in common that they are able to form objects layer by layer. Some of them are ink jetting processes. Some of them are actually using lasers to selectively melt powder. We have other technologies that actually use ultraviolet light to selectively cure resins layer by layer. And actually, again, another company that we have in town, another startup, uses this technology, vat photopolymerization. So Skyphos uses that technology to make very, very small, very, very precise, like lab on a chip kind of devices. So this technology is not about just making Yodas about yay big, but they can shrink and make things very, very small. But because of our guests here, we're going to be focusing today a lot on this directed energy deposition technology, which is about making metal components at very large scales very quickly. So let me tell you a little about, for example, one quick other technology that will just to give you an idea of other ways that we print is this idea of using lasers to selectively melt powder. And we have a technology like this on campus. And it's probably one of the most commercially adopted metal technologies. But again, this is a quick video of what they're using as a laser to actually selectively melt metal powder. And you can sort of see that transition from powder state to a molten state. And then when it's done scanning, that image layer will push powder across to sort of recoat a layer on. And then they'll selectively scan again, and that will melt, again, that area of the layer, but it melts into the previous layer. And at the end, you're almost like an archaeologist. You have to dig through the powder to get your final part. And believe it or not, many of you have flown on commercial aircraft with some components made from this technology. Every SpaceX rocket that you've seen go to space uses printed engines. We're seeing a lot of adoption and, both not even in not just aerospace, but even a lot of medical implants. Some of you might have friends who've had a spine implant or even a knee implant that has been printed with this technology, right? So It's not just plastic trinkets, it's actually also high-end polymers and high-end materials, but also metal components. So just to give you a flavor for other technologies. Again, as I mentioned, we're going to focus a lot today on directed energy deposition, which is this idea of directly adding material selectively. And one of the technologies we'll talk about is this opportunity. Imagine just taking a welder, attaching it to a robot, but instead of just doing one line of a weld, but actually stacking the welds layer by layer and building big metal parts out of that. And so Alan Pierce from FastTech will tell you a little bit more about that technology and how his company uses it in the production of large-scale metal parts. Another directed energy deposition technology I'll let Nancy explain is actually a very proprietary technology that actually was commercialized and invented here in the New River Valley thanks to MELD. And it's a really unique technology that takes another joining technique, in this case, friction stir welding, but does it layer by layer to make very large metal parts. Before I pass it off to them to explain their technology and their ideas and markets in more detail, I just wanted to quickly give you an idea of how these technologies are used. So when I first started this technology way back in the day, we called it rapid prototyping. It was only really a technology for quickly making an object, making sure everything looked right, and then sending it off to the machine shop to get made. But now we've transitioned to this world of additive manufacturing, where we look to these technologies to make final parts. So the original idea, and still a very big use of these technologies, is I have some sort of idea. I don't want to invest the time and money and tooling required to make that idea, but instead I want to go to a computer model and then hit print, right, and get a plastic version, a quick prototype, right? And it allows me to iterate through my ideas much quicker, or I can bring them to my customers and show them a model and say, yeah, so we all sign off on this idea. So it helps with communication aids as well. Again, a very great use of the technology. But then what we're starting to see is people starting to do more functional uses of these systems. So one of the big ideas is maybe I still am going to use traditional manufacturing to make my product, but I have a lot of tricky operations. I have to do assembly, so I have to sort of jig and fixture everything in place, or I have to do very careful inspection. And I don't want to use my manufacturing tools to create these custom odd-shaped fixtures. I can use this technology to sort of design and quickly make those kinds of jigs and fixtures to hold my parts in place during assembly or inspection, or to aid in traditional manufacturing. So that's another big use case we see in this industry. And again, every single one of these is made with a different technology. Maybe some of them are made out of metal, some of them are made of polymer, some of them are made out of composites. Each one has its own pros and cons, and that's something we as a community can work together to help with. The other idea, the other sort of evolution of the technology is what we refer to as rapid tooling, where we're going to actually print a tool and then actually use that in traditional manufacturing to make the part. So we're not making the part, we're just making the tooling and fixturing to finish that. So we might be able to make, for example, a short run injection mold using a polymer additive manufacturing process. So we're just making the mold and then inject plastic to make the final part. There are even technologies that allow you to directly print sand and use it in traditional sand casting. If you don't want to make the patterns and tools, you actually can print the mold directly. And even there are large-scale polymer additive manufacturing technologies that are being used to print very, very large molds, like this wind turbine blade mold, that they can then use to do conventional carbon fiber or glass fiber layup to make wind turbine blades or other very large-scale air structures. So additive manufacturing is not just something that fits on your desk, it's something that fits in half your factory, right? It's very large systems that allow for the manufacture of very large objects. And again, what we're really thinking about and what often we talk about is this idea of using the technology to take a design, do the digital analysis, and then take it to production and actually use that on a final object. And I think Nancy and Alan will talk a lot about this instead of these really cute senior design projects from Virginia Tech. The last thing that might surprise you is that these technologies, specifically this directed energy deposition technologies, are really unique in that they're also able to repair parts. So it's not about just making an object from nothing. You could actually bring an existing object into your printer and repair or deposit material to repair holes or other damage. So for example, I might have this toothed gear here, and I can actually go in, with a directed energy deposition system and selectively weld in and add material, and then actually take it now to my machine shop to remove material. Or again, re-tip turbine blades, for another example. And maybe Nancy will share some of her company's work in repairing, aircraft components, that otherwise at that damage would have to be thrown away and started from scratch. And here we're able to just directly use that technology to add material. So what are the value propositions? And I think this is a good opportunity to let Nancy and Alan, so I'll just run through these. I think the bottom line here is we have an opportunity with this technology to digitally design and manufacture objects, which allows us to reduce the delays between new ideas. This other idea is that complexity is not necessarily free, but we're able to make much more complex and lightweight components than other traditional manufacturing processes will allow, because we're able to sort of grow parts and not have to reach in and subtract and mill away. We're able to make lots of parts in a single print that are all unique. And some of your friends might have custom-made hearing aids. Almost all the hearing aids now in production are all 3D printed, right? Because each ear canal is unique. Some of you might have the Invisalign orthodontics. Those are also printed components. And this idea that we don't have to delay manufacturing, it's very agile. We have a single tool to make almost any shape, and that saves a lot in production time and training. And one of the really nice things, it also reduces assembly, because again, that complexity allows us to make a single part where maybe we had to make several components and then have to assemble them together. And one of the things that we're excited about is limited waste. So, if I were to take a traditional part that I would like to achieve, this part over here, traditionally I would take a giant block of metal and waste almost 20-to-1 ratio of the raw materials on the floor to get to the shape I want. Whereas an additive, we're able to get a much better buy-to-fly ratio, meaning the amount of material I purchase actually ends up on the part instead of just waste on the floor. And I think what you're going to hear from Alan and Nancy is that what we're really seeing right now, especially in the world of large-scale metal additive manufacturing, is that there's a lot of demand for large parts that are traditionally made through castings and forgings, and there's a huge supply chain limitation there. And now their technologies are providing answers to address that. So with that, I'm going to skip my last slides and just pass on to I'm going to keep calling them our assets, our key partners in our region who are really leading the industry with their representative technologies and services.